In the third part, so we are going to implement RNN model, right? So, and also we are going to convert text into vector. For this purpose, we are going to use a tokenizer from TensorFlow. So in this particular part of the video, we are going to use only library called TensorFlow. In the TensorFlow, we have a method called tokenizer, which will convert a text into simple vectors, or we can say from a array of string into array of numbers, right? So we are creating a word bank. So here you can see that we have taken 5,000 words, frequently used, top frequently used 5,000 words, and then we assign numbers, unique numbers to those 5,000 words. We can also increase those 5,000 words. Consider this as a word bank in which there are only 5,000 words. Each word has a unique number 0, 1, 2, 3 up to 4,999, right? And then we are converting numbers. We are converting a text into numbers in this X-train data, right? And then we are creating that word index. With that word index, we are converting our X-train into an X text into a vectors, right? So you can see that. And then there are different in lengths between those reviews. We need a common length, right? We need a common length. So we are fixing a maximum length of 200. So any text more than 200 will be truncated, or if that text contains less than 200, then we will add some padding. So we will add some zeros to make it as a 200 statement. Okay. Right, done. So here we have defined our RNN model. So this model RNN has we are using LSTM variant of RNN. So long, short term memory is a full form of LSTM. It's a one of the variant in RNN. So we have taken a two layer of LSTM and one layer of embedding layer in the model. So we can see one embedding layer followed by we have a 20.2 percentage or 20 percentage dropout, and then we have LSTM, again normalization, again LSTM, and then we have a final output layer. So here we have mentioned two because we have two classes, positive and negative. So based on the number of classes, we need to change this output layer. And then we have compiling our model with categorical cross entropy loss function. Since it's a multi-class, since it's a binary class, we can also use binary cross entropy, or we can use this, and then we are calculating accuracy. Now we can see this is our model, and the model has total close to 818,000 of parameters, right? So this is our first layer, embedding layer, where we have input dimension is, right, 5,000 words maximum. We have a 5,000 words in our embedding layer, and then each in length maximum of 200. And here, so we can change this epoch because each epoch is taking more than 1.5 minutes. We can just have already trained, and there is no improvement after certain epochs. So we can just have one or two here. So you can see the inputs into this RNN model training. So fit is what we are training the model. So in this RNN.fit, we have given almost 4 data points. First one is extrain padding, which is a padded data of input, extrain pad. This is, so here we have this converted text of truncated or padded up to 200 length, and then corresponding label. And epochs are nothing but iterations, 2 iterations or 10 iterations. So ideally we give between 10 to 30. That's why you get a stable performance. Since each iteration is taking more than 1 minute, we can have one or two. And then batch size is batch size. You can always have a 64, which is the optimum number. Okay? The more batch size, and it will consume more RAM, right? So less batch size, it will consume more time. So ideal batch size is 64. And then for validation data, I'm giving our test data, X train pad, and then again corresponding Y test. Once this training is done, then we will evaluate the same model with this test data, right? So we have a train data to train, and then we have a test data to evaluate. So you can see the training accuracy is 52 percentage, and then validation accuracy is 49 percentage. So if you make it 20 or 30, you get a stable uh, accuracy. And for this, we are using activation, ReLU activation in the hidden layer, and softmax activations in the output layer, because we are again, so we can, it's a multi-class scenario. We converted into binary class, so you can use sigmoid or softmax. So since if you are clear with binary class, then you can go with sigmoid. If not, we can also use softmax. Now, the first iteration, first epoch took 87 seconds to complete, right? For that, we got a loss was 0.69. So loss value should be 0, accuracy should be 100, right? That's how ideally the loss value that we are expecting is 0, right? So the close to 0 is better, right? Again, close to 100. So you can see the increase in the accuracy, right? From 49, it went to 56, right? So that's what. So if we add more epochs in our training, then more in the epochs in the sense somewhere between 20 to 30. So there is a better chance to get a better accuracy. So our training, the second epoch took close to again 68 seconds. Now this is a function to draw the confusion matrix, right? From the confusion matrix, we can easily calculate all the true positive, true negative, recall, and precision. And then followed by here we have our evaluations, right? RNN prediction. So we are giving only the test input to that RNN model dot predict, right? And then we are calculating the accuracy scores. We are drawing the confusion matrix with the help of a scalar library. Yeah. So once training is done, so I can execute this. We got so the prediction is done. So the model could predict uh, the precision for negative class is good, whereas the recall for the positive class is good, right? And then overall accuracy is 57%. Yes, because we train only for 2 epochs. If we train more than 20, then we can get a better accuracy. So this is how our confusion matrix looks. So this is true positive, and this is true negative, right? So this is false negative, and this one is false positive, right? So based on this, we have our recall, precision, and F1 score. Now it's real-time testing. So again, whatever we have done in the training, we have to do the same thing again in the testing. Again, cleaning, tokenizing, converting into a numbers, maintaining a maximum length of 200, and then we can send to. Yeah. So I have taken two review. One is positive, another one is negative. I'm sending these review to this function. This function will do all the mentioned process. Here we are cleaning, and then we are tokenizing, followed by we are padding to the maximum length, which is 200. Once padded, we are sending to our model for prediction. If the result index is greater than 0, index is greater than 0 is positive. That means index is 0 is positive, if not negative. We also calculated the confidence score. Now if we execute these things, right? So since we have trained only for 2, so we are getting a wrong results. Now what I'm going to do is we are going to add make into 10 epochs, and then we see how much accuracy we are getting. Of training, so you can see the validation accuracy increased from 78 percentage, and then you can also see the training accuracy increased into from 70s to 92 percentage, right? So though we still have the validation loss close to 0.6, but the training loss are close to 0.2. Now we are going to do the same prediction, evaluation for our test data on this 10 epoch training. So you can see now we got 79% accuracy, and the model can easily understand positive and negative review. And ideally, these two diagonals we should get 0, but now we are far more better than the previous version. And then now we are going to do the same review analysis of both positive and negative. Now we can see model can easily identify the second review as a negative and the first one as a positive. And now you can also see the confidence score, which is 90% for the second and 75% for the first one, which means the model is 75% confident about the first statement being positive. Whereas for the second case, it is 90% confident that this review statement is negative. Thank you.